All right, so today we have a new way of defining the sine, cosine, and tangent of an angle theta without relying on the unit circle at all. So all we need for this is any point xy that the terminal side of our angle theta passes through. So we have an angle, we're just doing it in the first quadrant because it's simplest. It passes through the point xy. First, we're going to let r be the distance from our point to the origin. So let's label that. That's this side here, or just the hypotenuse of a right triangle. So from either you can think about it as the distance formula or the Pythagorean theorem, however you think about it, we know the distance from the point to the origin. It is square root of x squared plus y squared. Right, this horizontal distance is x, this vertical distance is y, so we have x squared plus y squared equals r squared, or r is just square root of x squared plus y squared. All right, so now just from what we know about SOHCAHTOA, we can define sine theta just in terms of this stuff we have in front of us. The sine of that angle is opposite over hypotenuse, so the opposite side is y, and the hypotenuse is r. Same deal with cosine. We know the cosine of that angle is adjacent side over hypotenuse. So the adjacent side is x, and the hypotenuse is r. And we know that the tangent of that angle, TOA, so tangent is opposite over adjacent, so that's just y over x. And that's them. Those are the point and the plane definitions of sine, cosine, and tangent. You don't have to memorize that, but it will come in handy later on when we do polar coordinates. And as I said, it's just a different way of defining sine, cosine, and tangent of that angle without relying on the unit circle at all. All right, so here's a quick example. Theta is some angle whose terminal side passes through the point -3, 2. So that's what that looks like. So theta terminates in the second quadrant, but we don't actually have to worry about any of that stuff with these point in the plane definitions, and we want to find sine of theta, cosine of theta, and tangent of theta. So the only real computation we have to do here is first we have to find r, we have to find the distance from theta to the origin, and that comes right from the distance formula. It's the square root of -3 squared plus 2 squared. Be careful with parentheses around that -3 because you cannot get a negative number under that square root because r is a distance, so it's always positive. So that's what? The square root of 9 plus 4, which is the square root of 13. And then from here, you're just applying the definitions. So sine of theta is y over r, so the y coordinate is 2, so that's 2 over the square root of 13. Notice that in the second quadrant, sine should be positive, but since the y coordinate is positive, you don't have to worry about that at all. So it just works itself out. So I guess I'm going to do a quick rationalize on that one. That's 2 times the square root of 13 over 13. All right, same with cosine and tangent. Cosine of theta is the x-coordinate, which is -3 over square root of 13. Same deal, we would expect cosine to be negative in quadrant 2, and it just is, so that's -3 times root 13 over 13. And then tangent of theta is even simpler. It doesn't involve r at all. It's just the y-coordinate over the x-coordinate, which is -2/3.